just to finish off, I just wanted to just talk a bit about thermal storage, because it does have a role to play in terms of energy strategy. And it's worth, we spend lots and lots of time in the UK talking about electricity supply. But in actual fact, the gas system delivers about twice as much energy, nearly twice as much energy as the electricity system. Most of the energy in the UK is used for heating houses, and lands up as heat. And heat systems have exactly the same issues as electricity systems, in terms of you've got a peaking demand, but you want to try and smooth that demand out. The smoother you get it, the better the plant's going to be. So maybe it doesn't have the fast response issues that the grid has, but it still has that load shifting issue. And this is especially true when you come to plant like biomass systems and solar thermal systems, where you're trying to move heat from one period of the day to another. And biomass plants don't like, because they're very slow response. And so if you've got a changing load profile, which you might have if you've got lots of domestic housing on it, then it's good to be able to smooth that out. Solar, because it comes in the middle of the day and everybody's out. So it's exactly the same as the electricity system. So there is a role for storing heat. And it's worth noting that all across Northern Europe, we all have pretty much the same sort of climate. So whether you're talking about Northern Germany, Scandinavia, Northern France, we've all got pretty much the same sort of climate. And there is also a requirement for storing cooth, which is the other side of this particular coin. And in hot climates, you've got exactly the same problem, whether it's refrigeration or whether it's for air conditioning. You can have peak demand times, and you want plant to be able to ride through that peak demand. So storing cooth, i.e. not heat, but something much colder, it can also have some benefits for plant as well. And then we'll also look at, can you move heat from the summer to the winter? One of my favourites. So thermal energy storage, TES, can be done by a number of different processes. You can either store heat by a temperature change, either heating or cooling. So I could, for instance, just cool down a bit of this building. If I cool down these walls, they're nice solid walls. And if I cooled them down, I could effectively use that as an energy store or warm them up. And that would just be using a simple temperature rise or fall. And you could do the same with cooling. But the other kind of way of storing heating and cooling is as a phase change. So can you change something like water to melt or freeze, or can you get it to change from a liquid to a gas? And at that point, that latent heat of vaporization or freezing, that's another way of being able to store heat. And basically, you reverse those processes to release that heating or cooling effect. And there are a number of different options which we're going to look at. We can use thermal mass, just use the weight of materials to do it. We can use water, which is a fantastic energy store. And we can store water in tanks, or we can use it underground, or even in aquifers. And then we can use phase change materials, and this can be everything from water to waxes to a whole raft of different materials to molten salt. They can all be used as heat stores. So the energy you need to heat a volume of a material is going to be the mass of that material multiplied by the specific heat capacity multiplied by the temperature difference from the start to the finished temperature. So if I know the thermal capacity of this material, that's the amount of energy it takes to heat it 1 kilogram up by 1 degree Kelvin, then if I know that, and I know how much it weighs, and I know that I'm heating it up from 10 degrees to 15 degrees, I can calculate the amount of energy that I store. If I can't change the mass, And the only thing I can change is the temperature difference. If I have a very small temperature difference, I don't store very much energy. That difference between T2 to T1. You'll hear me talking about delta T, and that's what I mean. It's the temperature difference between the start and the finish. If you want it in volumetric terms, then you need to include volume and density to come up with this mass. That's what the rho and the v are doing there in that second equation. Make sense? So these are examples of buildings that have been built in a deliberately heavy way to increase their thermal mass, as it's referred to. And thermal mass can store energy over days or even over periods of years, depending on how you decide to use it. In this particular case, this is a building at Cap. These walls are made out of rammed earth. They could have been made out of concrete, but concrete's quite polluting and they wanted to build an eco building. And this is just earth, which is rammed into a solid wall about this thick. And it's about 8 meters high, that wall. And you can see the sun beats in on that. And normally you'd expect that space there to get really hot because you've got all of that glass. But because there's all of this mass there, it absorbs the heat as the sun falls on it, and it warms the mass up. So the air doesn't get really, really hot. What you can then do is you can use that to moderate the temperature in the room. It doesn't get too hot during the day, but then at night, it will also cool down again. It will sort of heat the building over the night. So it smooths the heat temperature profile of the building. You could also deliberately cool that mass at night. So during the day, if you're using this mass to keep the temperature down, you don't want to heat the building, you might ventilate that space at night. And what it will then do is it will cool the mass down. So the next morning when everybody comes in, everything's going to be nice and cool again. And you're ready for another bright sunny day. And you can knock a lot of degrees off of a building, knock 10 degrees off of a building by doing that cooling arrangement, if you have a big temperature difference in between day and night. So it works in sort of desert conditions. It works in our sort of climates where we have big differences between day and night. But if you go into tropical conditions where it's pretty much the same temperature as night during the day, it doesn't do you any good. You can't use it. Mass is not great in those situations. So it works very well in our sort of climate. We could create virtual mass. We could just use water as an energy store. And water's fantastic. It stores a huge amount. It takes a lot of heat, a lot of energy to heat it up, not very much. And because it's a fluid, it's very, very flexible. That's why, what people use radiators full of water. It's because water just moves a lot of heat for not very much mass. And it becomes a very flexible medium. So now we could be heating it from solar and putting it into a store. We can do all sorts of things with the water. And we can have it on all sorts of ranges of scale, from a few kilowatts worth all the way up to many thousands of litres. The problem with storing water is that you've got to put it in some kind of container, and there's going to be losses associated with that. So you're going to probably land up insulating it some way to try and ameliorate those losses, but there are always losses. Just the same as with our batteries, thermal stores have their own inherent loss. And as we increase the temperature of that store, that loss becomes more. So you might say, well, okay, I won't store heat from, sort of 20 to 30. I might try and do it from 20 to 100. Well, at 100, the losses from your store are going to be 5 times greater than they were at 20. So a common use of these stores are called accumulators. And they're basically just big hot water tanks, just like the hot water tank that you've got at home, or you may have at home if you haven't got a combination boiler. And they are heated up, usually off devices like heat pumps or biomass boilers, and both of which don't like variations in demand. And the idea behind them is that you can heat them up, in the case of a biomass boiler, up to maybe 90 degrees centigrade. You can then allow the boiler to go out, and you could then use the energy that's stored in this in this tank to keep your house hot for the rest of the day. So if you had something like a wood stove connected up to this, the flow and the return, you'd heat it up, you'd have the wood stove heating the house, it heats up this tank, the wood stove goes out because you've gone out, and the house would carry on being heated, you reverse the flow and you take it out. The key thing about these accumulators is that you need stratification. You want there to be a nice boundary in between the cold water coming back off of the system and the hot water that you've heated up off of your boiler. So that boundary there is really important. Otherwise, it all just gets mushed up. It could become, instead of getting a nice clear 10 or 20 degree difference between the two of them, you'll end up with only a couple of degrees, and that makes the energy storage less efficient. So you tend to want nice low velocities. When the water's being pumped round, in the tank itself there, it wants to be going nice and slow, because otherwise it just mixes it all up. And that's usually achieved just by making the tanks really big. So that's the sort of domestic scale. And at a domestic scale, you might be talking about, for a heat pump, you might be talking about something as modest as 500 litres, about 3 times bigger than your hot water cylinder at home, all the way up to a biomass boiler. 300 kilowatt biomass boiler might have 10 to 20,000 litres. One of the applications for these kinds of stores is on large-scale district heating solar schemes. And these are schemes where instead of putting solar thermal systems on the roof of your house, you've put them out in a field or it's on a block of flats, and it feeds heat into a district heating scheme. And so this just sort of gives you an idea of the sorts of sizes of kit you need. So if you've got 30 or 40 housing units with 60 people in them, that sort of scale, then you might be talking about 1 to 1.3 square meters of solar thermal per person, and you might be talking about 70 to 100 litres per square metre of collector area. So if we did have 100 people, let's go for 50, because then I might be able to keep that. We'd need about 50 square metres of solar thermal, and we would need something like 50 times 100. We need something like 5,000 litres of storage for that. And then that would deliver something like 350 to 500 kilowatt hours per square metre of solar storage. And that system might be able to supply 50% of the hot water demand and about 10 to 20% of the space heating demand. If you go to a bigger scale scheme, where you're talking about 100 to 150 housing units, and then you can, because they're bigger, you can afford to put in more solar collector, and that means that you're getting these sorts of yields, and your storage volumes can also become significantly bigger, and your total ratio is landing up at being anything up to 70%. So that's one way, and here's a bit of luck. There's an example of one of these systems. And there are quite a few examples in continental Europe. They haven't really taken off in the UK, and that's largely because our land price is pretty high. But this is a district heating scheme in Kungälv in Sweden. I think it's a town of about 5,000 people, and they have a 13 megawatt wood chip boiler in this building here, which does most of the heating during the winter, nearly all of the heating during the winter. But to back it up during the summer, because in the summer the biomass boiler is not very happy because it hasn't got very much work to do, they have a 10,000 square metre field of solar thermal collectors, not PV, solar thermal. And that all feeds into a 1,000 cubic metre buffer store, which is that whopping great tank there. And that's delivering, out of that system, they get heat at about 3 pence a kilowatt hour. Well, 3 euro cents, I beg your pardon, that's cheaper than 3p, isn't it? No, that's about a little bit more expensive. So yeah, so and when you consider domestic gas price at the moment is 4p, and then you put it through a gas boiler, so which is only running at 85% efficiency, it lands up at being 4.2p. You can see it's actually quite a good deal. The solar thermal.
Is it €29 the capital cost?
Sorry, no, no, that's per megawatt hour. No, that's the effective, that's not the capital cost, that's the effective cost of energy. So that's per megawatt hour. So divide that by 1,000 to land up with euros per kilowatt hour. It cost about £150 a square metre. So that's 150 times by 10,000. So it's about 1.5 million for the solar thermal plant.